Today we learn about limit of a function. Let fx be a real valued function. Then what is the limit of the function x at x tends to x naught? Okay, I will discuss this. First, let x naught plus delta and this x naught minus delta, this L plus epsilon, L minus epsilon. So this L plus epsilon, L minus epsilon, and this x naught, where x naught equal to x naught, this x naught plus delta, x naught minus delta, and this is delta. For x naught equal to x naught lie here in between this, and fx lie between this, either this or this. So fx lie between this. Here you want to learn what is the limit x naught tends to x naught fx is. So this is the picture. I will write the definition. So what is the definition? Except possibly at x naught itself. We say that the limit of fx as x approaches x naught is the number L, and we defined as limit x tends to x naught fx that equals to L. This the definition. That is, if for every epsilon greater than 0 there exists a delta greater than 0 such that for all x 0 less than x minus x naught less than delta, that implies modulus of fx minus L less than epsilon. So what is this? This is nothing but 0 less than modulus of x minus x naught less than delta, that implies x0 minus delta less than x0 plus delta. Okay, in our picture this x dot minus delta, x0 plus delta, and x lie in there. This is the definition and this is the picture. And limit exists if L minus epsilon less than fx less than L plus epsilon. That is, L minus epsilon, L plus epsilon, L, and fx lies between this. That is, if x naught equals to x naught lying there, then f must be lie between this. If this happened, then a function fx has a limit at x tends to x naught, limit fx exists and is equals to L. So what is the definition? Fx be defined on an open interval about x naught, except possibility at x naught itself. If possible, at that point x naught, fx does not define, but fx is defined all on an open interval about x naught. That is, x naught at the point x naught may or may not be function defined, but x naught minus delta and x naught plus delta in this open interval fx must be defined. We say that the limit of fx as x approaches x naught is the number L, and we define as limit x tends to x naught fx equals to L. So our challenge be this: if fx be a function, this y equals to fx, then our challenge is to we find a delta which is depend on epsilon. Here epsilon equals to 1 by 10. So delta depend on 1 by 10, where here epsilon equals to 1 by 10. Okay, and delta depend on epsilon and x. So this is the challenge, to choose a delta which is dependent on epsilon such that the function lie between this area. Okay, then we say that limit x tends to x naught fx equals to L exist. Here delta equals to delta 1 by 10, where a number. Let us solve some example. So this using figure. So draw this figure. So this 1 plus epsilon by 5 and this 1 minus epsilon by 5. 2 plus epsilon, 2 minus epsilon. Let the function be if fx on 5x minus 3, what is the limit at the point in x tends to 1 fx is here limit x tends to 1 fx, that equals to 2. I will prove this by definition. Let this 1 and this 1 minus delta 1 plus delta, okay, and this 2 minus epsilon and 2 plus epsilon, this 2. This is the function fx. This is the function fx. Here we choose delta. So here how to choose delta? So x minus 1, this less than delta, that implies modulus of fx minus 2 less than epsilon. Okay, so what is the value of delta? So what is the fx here? Fx is nothing but 5x minus 3. So that implies modulus of 5x minus 3 minus 2 less than epsilon. That implies minus epsilon less than 5x minus 5 less than epsilon. That implies 5 minus epsilon less than 5x less than epsilon plus 5. Okay, now divide by 5. 1 minus epsilon by 5 less than x less than epsilon by 5 plus 1. Okay, so we choose this delta. This is the delta, that equals to delta, that implies modulus of x minus 1 less than epsilon by 5. So epsilon by 5, that is to delta. So in this example we find delta. What is the value of delta? Epsilon by, which is dependent on epsilon.